had covered yesterday. So I request any one of you please confirm if my screen is visible to everyone so that I can start. Yeah, just leave me a confirmation. My screen is visible. Okay, okay. Thank you, sir. Thank you. So what we covered yesterday is we had a brief introduction about CFD and ANSYS Fluent. Uh, then we saw how we can clean up the geometry and prepare it for the CFD analysis using space frame, and also we mesh that geometry so to discretize the whole domain so that it can be sent to the solver part. Now today what we will do is we will set up the solver, solve our problem, and we will post process the result. So let me just share what we did and what geometry we have taken. Let me just share the complete screen now. So this was our geometry. I hope my screen is visible. So this was our geometry. Uh, we had a fan inside a casing, which was basically an exhaust fan, and we wanted to see and analyze the flow through this exhaust fan. So for that, yes,
हाँ ये तो हमको कंफर्म है कि तुम्हारा प्लेसमेंट कोऑर्डिनेटर वाइज भेज दिया होगा ठीक है लेकिन नहीं भेजा था
so what we saw that we prepared this particular geometry. We made an MRF, which was nothing but a cylinder enclosing the fan and a fluid domain, which we made like this, like a box. We shared the topology between the fan and the fluid domain. So basically, this fan was enclosed inside an MRF, which will be the moving domain, and the fluid domain will be the stationary one. And after that, we mesh this particular geometry using fluent meshing, right? We selected the appropriate size, the minimum element size and the maximum element size. Okay, we generated the mesh. Then we described the geometry, like if our geometry is having only solid regions, both solid and fluid or only fluid regions. Okay, we updated the regions where we defined that this fan and the casing are dead regions, and this fluid domain is fluid domain. Basically, type of region is fluid, and MRS will be also be the fluid. Now, and after that, we generated the volume mesh. Okay. Now, I will show you there are two methods by which you can share this mesh or send this mesh to the solver part. The first method is that you can just click on this switch to solution option, and then this fluid measure will be uh, get open into the solver setup. Or there's another method. Suppose you have meshed this particular geometry, and you have selected different sizes for the same geometry. So for that, you can just save this mesh by clicking on the file option, right mesh option, and it will save the mesh in a particular location. I have already saved this particular mesh. So you can open, you can save this mesh like this. Okay. And after saving this mesh, you can just go open Fluent from the uh, search box in Windows taskbar. You can click on solution, read, mesh, select the particular mesh, and select the number of solvers you want to use for solving, and just click on start. So you start the Fluent solver setup. Okay. And the other method which I told earlier is you can just click on switch to solution. So I would be using this. So once you click on switch to solution, it will ask you if the mesh is valid as per the quality parameters that we discussed yesterday, like the minimum orthogonal quality should, the list or orthogonal quality should be greater than zero point 0.1. If we talk about fluid meshing, different solvers have different quality parameters criteria. Okay, so we'll just click on yes, and it will start to open the solution or the setup or the solver, Fluent solver. Okay, now you can see here that it is showing done. And mesh is now scaled to meters. So what you see in front of your screen is the Fluent solver, where you set up your solver by giving various inputs as per your objective or as per your project, whatever you want to perform based on the geometry and your requirement, and you solve this particular problem. You have the first option that is there is the general, where you select where you check the scale of the mesh, check the mesh, report the quality of the mesh, display the mesh, or you or also set the units. So by default, the angular velocity that we will be taking is in the radians per second, but we will be giving the value in RPM. So we can change that also. Okay, you just go to revolutions per minute and just close it. And similarly, there are a lot of other quantities where which you can select for different units. Suppose if I talk about length, so length had different units like meters, millimeters, centimeters. So you can change the units for length as well, right? Like meter, centimeter, millimeter, inch, feet. Okay, so we will take for our this particular problem. And then we have so type you can also select what type of solver you want to use, pressure based or density based. So mostly for incompressible flow, we use pressure based, and density based is mostly used for the compressible flows, or you can say for aerospace applications or high speed applications. Okay. Then we have velocity formulation, whether you want to calculate the velocity in absolute terms or relative terms. Then also what you want to perform, like the steady state analysis or the transient analysis. Okay, and also the gravity. If you want to perform certain analysis such as natural convection, where gravity is dominant, or flowing of water under the action of gravity, then you have to turn on the gravity. But since we are performing a forced kind of flow, like we are using an external agent that is driving the flow, such as a fan, so then we don't need to perform. Then we don't need to select gravity option. So let us just display the mesh. It is selected face. So it will show all the faces which are there in the mesh. Like you can see here, it is only showing the fluid domain, because other things are inside this particular box. So if you want to see what are those inside it, you just need to click on the edges and unselect the faces, select outline, and it will show you the internal parts. What are all there? Okay. It will hide the face, it will just show you the outline. Then we have the models option. Okay, you can see here that we have different models available, multi-phase, energy. If you want to perform thermal analysis, then you just need to turn this energy equation on. Okay, multi-phase, we have option for performing multi-phase analysis with these models, VUF model, mixture. A mixture is mostly used for evaporation, condensation, wet stream, oil area, we have these four models for multi-phase analysis. Then we have models for viscosity of the flow, whether it's in viscate, laminar, spalart, maras, K epsilon, K omega, and for these also we have different models: K epsilon, standard, realizable, RNG, K omega. We have standard, generalized K omega. So this GECO, it is developed by ANSYS only, and BSL, SST. Okay, so we have different models for turbulence, or you can say for capturing the turbulence in the flow. And we have also LES and detached eddy simulation, but these are generally used in aerospace applications. We don't require these as of now, because we simply solving a certain simple problem here. So we just select the default viscous model. We also have models for radiations, heat exchangers, Discrete phase, suppose you want to see discrete phase are nothing but particles, how particles are getting mixed inside a liquid or gas. Then you can use discrete phase model, and you can just select the injections. Okay, it will inject the solid particles inside that domain. We have acoustic, we have a structure. Acoustic is mostly used for aeroacoustic. Okay, the acoustic is also different type, aeroacoustic, vibroacoustic. So here it is mostly related to the aeroacoustic. Suppose you want to see, like, if you are manufacturing a particular drone and you want to see if my drone is operating in somewhere, how much noise it is producing and what amount of noise is being perceived by people standing at different locations. Then you can use this kind of model. We have used this kind of model in one of the problems when we were helping with one of our clients. And you also have Eulerian wall frame. This is basically used for the open channel flow. Then we also have battery model. Now a lot of people are working in lithium-ion batteries. So this model is provided inbuilt inside Fluent, where you have the option to perform battery and lithium-ion battery analysis. You can see here. Let's just show you for knowledge purpose. Solution method, we have CST coupling, FMU, MSMD. So this is the solution method, and these are the electrochemistry method model. So these are also there. We can talk about this based on the your requirement. If you want to learn about battery modeling, then we have materials option where we can set a wide variety of materials available in Fluent database. For fluid, we have acetaldehyde, acetone, air, alene, aluminum arsenate. So a lot of gases and refrigerants are also there to see to perform analysis. Okay, atomic oxygen we have C5H3, calcium carbonate, carbon dioxide vapor, carbon monoxide. So carbon monoxide you can use for pollution analysis or smoke analysis. Okay, and let me just show you the most used, which is water vapor, water liquid. Okay, these are all there. We have also material library for solid, mostly use solid app for fluid applications like gold, gypsum, nickel, steel, titanium, wood, aluminum, copper. Most of the refrigerants flow inside copper tubes, so this is also there. Okay, since we are performing analysis on air, we will just select the air. Air will be selected by default for solid. Sorry, for fluid, and aluminum will be selected by default for solid. Okay. Then we have cell zone conditions. So cell zone conditions are nothing but the domain that you have made. So this is the reason why I have named them MRF and fluid domain while we were making while we were preparing the geometry for fluid analysis, so that it will be easy for us to work to spot the particular zone and give it the values. Because suppose this is a simple case. Okay. Now suppose you are performing analysis where a lot number of domains are involved. So in that case, it will be very difficult for you to spot that particular domain, because what happens is when the designers, when they design these kind of parts or components, they just give generic values, or the software gives generic values or generic names to these parts and components. So it becomes quite difficult for you to spot and give a particular desired value to these components. So that's why it is very important to name your component while you're preparing your geometry for CFD analysis. Okay. Now we have boundary conditions. Boundary condition for inlet, outlet, internal. So you can see internal fluid domain, interior MRF. Okay, so this is the internal or the interior of that particular domain. Now we have wall like fluid. This is the wall for the fluid domain. This is wall for the fluid domain, which is the casing part, fluid domain. Now you can see that this wall is named by fluid domain and MRF. Two, both of the zones are there in this the name of the wall. So whenever you see this kind of a name given to a particular wall, you should understand that this is nothing but the interface between these two zones. Let me just show you. You can see now, this was the thing that was shared or that was visible when we did share topology. Let me just show you. You can see it. This particular blue lines. So this is the wall which is being shown here. by the having the name of both of the zones. So what we will do is, since we want to make the solver understand that the physics has to be transferred from the fluid zone to the MRF. Let me just show you that mesh again so that you can understand easily. Yeah. So what we need to do is we need to make the solver understand that the fluid or the physics has to be transferred from this MRF to this fluid zone or from this fluid zone to the MRF. So what we will do is we will make this wall as an interior. By doing this, the solver gets to understand that this is not a wall and certain things has to be if flowing through this particular wall. This wall is not a stationary or an wall, opaque wall. Okay, so this is why we have made it an interior. And I would request everyone, if you have any question, just you just write down that question in the chat box, okay? And we will discuss after our session. So once we are done here, let me and this is the fluid domain. So we can also change the material for this fluid domain. We just need to double click on it, or you can also do this by double clicking on the cell zone conditions, and it will open up on the task page. And you can see here, suppose by default this fluid domain has been selected as solid, then you can make it as fluid here. Also for the MRF, and you can change the fluid which is inside this particular zone by clicking on edit option. You can see here now material name, air, because fluid has only air, fluid consisting only of air, material as air, that's why it's showing air. So let me just take another material just for the demonstration purpose. What we will do is double click on materials, create an edit, go to fluid, we will select fluid option, and we just select another medium. Let us just take something which is nitrogen, or let us take something else. Uh, it's in gaseous form. Dioxygen. Let's just for example, dioxygen we take. We just copy it, close. Okay, then close. Then again we will go to cell zone conditions. Click on fluid domain, add it. Now it will show up the other material as well, dioxygen. You can see here. So similarly, you can do this. You can also click on materials, delete this particular fluid material. Okay, you can see that it has now been removed, and it will not show now in this particular fluid zone. Okay, just click on apply and close. Now we have to give the rotation value to this MRF. I would request everyone to please mute yourself. Saber, can you please mute yourself? Yeah, thank you. Uh, yeah. So this is the place, or this is the option by which you can give rotation values to your particular zone. So one is the way that I have told you, that you just need to double click on this MRF, you just expand it, click on this particular zone, or you can just double click on the cell zone condition. It will show up here in the task page. Click on MRF and then click on edit. Now the particular zone name is MRF. So we need to give rotational value. There are these many options which are being shown: a frame motion, mesh motion, 3D fan zone, source term, fixed values, laminar zone, porous zone. So these are all there for different applications. And there are two things that you can see here with motion: frame motion and mesh motion. So these are for different analysis type. For steady state, we go for the frame motion. For the transient state, we go for the mesh motion. Okay, like I shared with you yesterday, that we don't need to make shape topology in case we want to perform transient analysis. In that case, we need to create interfaces. Okay, so what we would do is we select the frame motion. Now you can see we have different options available here: rotational velocity, rotation axis origin, translation velocity, in which what would be the axis of the rotation. So you can see here from the triad that our fan's axis coinciding with the z axis. Okay, and it is already taken as one. So suppose the axis would have been coinciding with the x axis of the triad. So what will we do in that case? We will make x as one and z as zero. But here it is coinciding with the z-axis, so we will just type 1 in z and 0 in x. Okay. Now, since you can also give zero values here, rotation, axis, origin. If you can see here, it will take, because there is only one single MRF zone. Now, suppose there are different MRF zone in your component, then you need to see like what would be the axis of rotation. So in that case, you can find out that axis of rotation using space flow. What you can do is you just hide the fluid domain, or you just show only the MRF zone which is on the screen. Go to the measure ribbon, click on measure option, click the MRF, and it will show you the X value, Y value, Z value. Okay, and you can just put this value in the Fluent solver. That is the distance from the x origin. And for the rotation axis, the axis of rotation, you need to select the mass properties. Once you are there in the measure ribbon, you just click on mass properties. It will show you the center of volume here, and this center of volume is nothing but the origin which you are seeing here, the origin of this particular MRF. And what you are seeing here is the distance of this particular MRF from the origin of this whole uh, you can say sheet on which it is being drawn. So we select on the select the mass properties, and we see the values here. So hardly it is away from the origin. It is 0.0019. So you can take this value here in this fluent solver, 00, and what was the last one? What is that? 1.0019. 1.0 sorry, 1.0019. Okay. So for the, and then we also have to put the speed, rotational speed. So I want this value from you people. Uh, Please let me know what is the actual range of exhaust fan, rotational value of exhaust fan. Let me see what are your answers. Let me just check. Just put in the value that you think that should be the rotational value for the exhaust fan in the chat box. Let us see. I'm waiting for your answer. Come on, people, just hurry up. We don't have a lot of time. Just give me a value for this rotational, so that I can put in the rotational velocity. Any answers? Any guess? No. 1.5 is very less. A fan doesn't rotate 1.5 times in 1 minute. Any more values, people? I'm waiting for you all. Just give me a value. No, not. It's not. It's greater than 1,000. 350 RPM is mostly for fans, passive ceiling fans. This is exhaust fan. You need to create suction. I'm giving hint also. Higher than 1,000. Any values? Any guesses? Arbaz, Daniel, Asad, Somik, Anis, Shahryar, Ehtisham, Faisal, Vikas. Give me certain values, please. Rayan, Amir, Sabir. Are you all there even? Mukarram Ali, Alkama, Vivek. Give me a value, please. Devjit, Ehtisham, you are close to a certain value.
Yes, sir. Yes, sir.
Yeah. Faisal, you are very close. Good, good, very good. So I will move ahead with Faisal's value. Mostly it is close to 2000 only. So let us just take 2100 for this for this case. So let us just go through again that we have taken frame motion, the rotation axis we have given, origin for rotation axis, rotation velocity we have given, we have selected a rotation axis direction. There is no translation velocity, so we are done with the MRF zone. So click on apply and close. There's no need to, I have already informed you about the boundary conditions. As if there was any flow through a pipe or a certain domain where there is inlet and outlet, then that would also be showing here based on how you have modeled it in your geometry. Okay. So we don't need to worry about mesh interfaces. We don't need to worry about reference values, reference frames. Now we will be going to the solution part, or you can go to the, you can move, see, there are two ways you can move in Fluent, either from left to right on the top or from top to bottom on the left side. This is the outline view and this is the ribbon. We have domain, physics, user defined functions, solutions, results, view, parallel to see how much CPU usage is there, parallel design. Okay, so a lot many options are there in this particular solver. Now we will be going towards the method option, which is a very important method, or you can say the option that we need to set for the solver. So solution method is nothing but the algorithm by which you will be solving those algebraic equations. I told you yesterday, na, the governing equations are are solved on the discretized volume or the volume which has been divided into number of parts, and those equations, those generalized equations are converted into PDEs, and these PDEs get converted into algebraic equations, and these algebraic equations are solved through particular methods or algorithms to give you the result. Because this is nothing but an iterative process, like the numerical scheme that you must have learned in your bachelor's and master's. So there are number of methods available. Simple C, piso, coupled. So simple nothing but semi-implicit method for pressure linked equations. What we do is we create a coupling between the pressure and velocity. Okay. If I talk about simple method, na, we guess a value for pressure. Okay. First we guess a value for pressure, and by using that we solve the Navier-Stokes equation. And when we solve the Navier-Stokes equation, we get certain values for velocities, and we compare these velocities with the guess value, and we move ahead in the similar way. And once we do this, we make sure that the error between the guess value and the right or the actual value is very less. So these are called residuals. So what I can do is I will show you by this both methods, simple and coupled. So simple is a segregated solver, coupled is a solver where both the continuity equation and the momentum equation are solved simultaneously. So simple is quite fast, but may give sometimes give floating point error. And coupled is also used. Coupled is slow, but it avoids a lot of floating point exceptions. Okay, or you can say in
Yes.
simple was diverging of your solution. Yes. Any doubt, anyone? I just see someone is saying something, trying to say something. Any issues, anyone? Any issues? Are we good to go ahead? Please let me know. Are you people there? Guys, come on, please make the session interactive. I don't want to be one-sided session. Anyone there?
Yes, sir. Yes, sir.
Okay, Anil is there. Anis, Faisal is there. Vivek, you there? Alkama, Ihtisham, are you people there? Vikas, yeah. Soumik, Sharyar. Okay, okay, okay. Thank you,
Everyone
thank
there.
you.
Everyone.
Yeah, yeah, okay. So let us just continue. So what I was sharing with you all that the methods are nothing but the algorithm through which these equations are solved, since these are iterative process. Okay. So let me just go with the simple method first. You can just see these are second order momentum. So these are the second order upward. So these are nothing but methods, or you can say these improve the efficiency or accuracy of the solution. We will discuss more about these when we are discussing the CFD deeply, when we will be learning about the CFD fundamentals. Okay, pseudo time is off. We will make warp phase gain correction on to make our solution more robust. And these are controls. So see, when we go
Sir,
through
this video is available in English.
okay, okay. Who is this? Let me just see. Who was this? Who is having any issue with doing this? Amir, is that you?
Yes, sir.
Okay, okay, Amir. Okay, yes. तो आमिर
ये
मैं ये कह रहा
इंग्लिश
था
में
कि
अवेलेबल हो सर?
ओके ओके तो आमिर व्हाट आई वाज सेइंग मैं ये कह रहा था कि जो मेथड्स होते हैं ये एक एल्गोरिदम होते हैं जिनके थ्रू जो इक्वेशंस होती हैं गवर्निंग इक्वेशंस वो सॉल्व होती हैं कंप्यूटर पे इटरेटिव वन बाय वन इटरेटिव प्रोसेस होता है इटरेटिव आप समझते ही होंगे तो उसी तरह से कई मेथड्स हैं हमारे पास जैसे सिंपल है सिंपल सी है पीसो है कपल्ड है
सर इंग्लिश में समझा सकते हैं सर आप?
हाँ मैं बता तो रहा हूँ
इंग्लिश।
आपको हिंदी हिंदी में भी तो बता रहा हूँ हेलो हेलो अभी गुड
जी
टू
सर।
गो बढ़ूँ आगे
जी सर।
ठीक है तो अभी हमारे पास आप यू कैन सी हियर दैट सिंपल है सिंपल सी है पीसो है कपल्ड है तो जो सिंपल होता है इट इज मोस्टली यूज फॉर स्टडी स्टेट केसेस स्टडी स्टेट केसेस में हम सिंपल यूज करते हैं सिंपल सी यूज करते हैं एंड पीसो पीसो इज जनरली यूज फॉर ट्रांजिएंट केसेस जो जहाँ पे टाइम मार्चिंग प्रॉब्लम होती है जैसे मल्टी फेज हो गया या कभी कभी जो फ्लो की प्रॉब्लम्स होती हैं वो ट्रांजिएंट होती है नेचर बट हम टाइम बचाने के लिए उसको स्टडी स्टेट में कर लेते हैं बट अगर हमारे पास कंप्यूटेशनल पावर है हमारा system is strong. Our system is strong enough and capable enough to perform that analysis in a reasonable amount of time. Then we can go for transient study, and in that case, PISA algorithm is used. Okay, and these are controls. So you can see here, आप देख सकते हैं यहाँ पे अंडर रिलैक्सेशन फैक्टर्स लिखे हैं. तो जब हम सेग्रीगेटेड सॉल्वर्स यूज करते हैं, सेग्रीगेटेड सॉल्वर जैसे सिंपल सिंपल सी, तो वहाँ पे अंडर रिलैक्सेशन फैक्टर्स आते हैं. और जब हम कपल सॉल्वर यूज करते हैं वहां पे क्वारंट नंबर आता है उस केस में जो कंट्रोल होता है या कंपैटिबिलिटी प्रॉब्लम होती है वहां पे क्वारंट नंबर आता है जैसे आप यहाँ पे देख रहे हो ना टाइम एक्सक्लूसिव रिलैक्सेशन फैक्टर्स ये अभी आपको क्वारंट नंबर भी दिखेगा मेथड में जब आप आगे जब सॉल्व करोगे तो वहां पे आपको क्वारंट नंबर भी दिखेगा तो अभी हम सिंपल पे सॉल्व करते हैं अभी आप इसको फर्स्ट ऑर्डर भी कर सकते हो सेकंड ऑर्डर भी कर सकते हो इसको भी बट जैसे फर्स्ट ऑर्डर करोगे आप तो सॉल्यूशन उतना एक्यूरेट नहीं आता है मतलब जैसे आप ऑर्डर बढ़ाते जाओगे आपको पता होगा जैसे हम फर्स्ट ऑर्डर इक्वेशन सेकंड ऑर्डर इक्वेशन थर्ड ऑर्डर इक्वेशन करते थे बैचलर्स में तो सेम चीज वही है जितना आप ऑर्डर बढ़ाओगे उतना एक्यूरेसी बढ़ेगी और उतना कंप्यूटेशनल पावर भी बढ़ेगा तो डिपेंडिंग अपॉन दीज फैक्टर्स यू नीड टू सेलेक्ट ओके और इसमें एक चीज ये भी है कि मान लीजिए कि आप ट्रांजेंट केस कर रहे हो परफॉर्मिंग ट्रांजेंट एनालिसिस इसमें टाइम लगने वाला है आप थोड़े इटरेशंस के लिए फॉर फर्स्ट फ्यू इटरेशन आप उसको फर्स्ट ऑर्डर पे चला दो जैसे मान लो 1000 इटरेशन हो गई 500 इटरेशन हो गई आप उसके बाद फिर उसको सेकेंड ऑर्डर पे मूव कर सकते हो तो दीज आर ऑल टेक्निक्स दैट यू कैन परफॉर्म वंस यू आर प्रॉपर्ली गेटिंग अ हैंड्स ऑन दीज काइंड ऑफ प्रॉब्लम or the industry level problem. So what we will do is we will keep these things as it is. And one thing also, you need to make sure that the sum of the under relaxation factors for the pressure and momentum should be 1. If you are making pressure zero point 0.4, you need to make momentum zero point 0.6. If you are making momentum zero point 0.5, you need to make pressure zero point 0.5. Okay, likewise. एंड रिपोर्ट डेफिनेशन सपोज आपको देखना है कि एक पर्टिकुलर पॉइंट पे मेरा फ्लो कितना आ रहा है, उसका प्लॉट आपको चाहिए, तो आप यहाँ पे वो भी आप बना सकते हैं, जैसे वॉल्यूम फ्लो रेट हो गया, एरिया वेटेड एवरेज हो गया, वेलोसिटी का। लाइकवाइज आप ऐसा उसमें बना सकते हो। ओके, इस तरह से मॉनिटर्स हैं हमारे पास, रेसिडुअल्स हैं। so these residuals are nothing but the error between the guess value and the actual value। तो अभी आप यहाँ पे बाय डिफॉल्ट 1 - 3 होता है, और एनर्जी के केस में 1 - 6 होता है। यहाँ पे एनर्जी दिखा रहा है, रीजन है यहाँ पे मॉडल में हमने एनर्जी ऑन कर दी है। ठीक है, गलती से आपको दिखाने के लिए मैंने ऑन कर दिया था शायद। तो हमें एनर्जी की कोई जरूरत नहीं है, बिकॉज वी आर नॉट सॉल्विंग एनी थर्मल प्रॉब्लम। जैसे ही आप एनर्जी ऑफ करोगे, यहाँ से एनर्जी का रेसिडुअल गायब हो जाएगा। 1 - 3 आप देख रहे हैं। आप इसको चेंज भी कर सकते हो, 1 - 6 भी कर सकते हो, 1 - 10 भी कर सकते हो। आप चाहते हो कि और आपके पास एक्यूरेट रिजल्ट आए और क्लोज टॉलरेंस हो, लाइक 0.00001 हो एक्चुअल वैल्यू एंड गेस्ट वैल्यू के बीच में एरर। ठीक है, तो आप इस तरह से कर सकते हो, depending upon your problem. And one thing is also I want to share with you all, if you're performing analysis related to heat exchanger, na, so there are certain cases where you don't need to see the convergence. So you can also turn off the convergence conditions also. Okay. And now we are done here. Now what we will do is we will initialize this particular problem. Initialization means giving the initial value.
No, sir.
like we we used to do na in Newton Raphson method, or Cayley this
सर
what we
ये आप कौन से सॉफ्टवेयर में शो कर रहे हैं सर?
this is Fluent. The main agenda which I shown you was for the Fluent tool. ANSYS Fluent. We will select the absolute reference frame. We will click on initialize. Once it is initialized, we will make a certain plane to observe the velocity. For that, we just need to go to the surface part, click on plane, select the plane in which you want to take a or create a plane. You can see here, this is the YZ plane. You just click on create by giving a certain name to it. I'm giving it X section. Okay, so just create it. Once it is initialized, you can observe the contours on this particular plane. Let us just see a contour. So this is also part of post processing. I'm making this because we need to create, if we need to create animation for this particular contour, we need to first create the plane and move this contour into animation part. I will show you that also. Just name it as velocity. Select the section, this display color map options. You can also do this by clicking on float, because we don't want values in terms of exponents. Yeah. Now you can see here that a cut section has been made, and we will see the velocity on this particular plane. If I just zoom in closely, you can see the values, because the velocity is maximum at the tip. V is equals to R omega. Okay. Now what we will do is we go on calculation activities, solution animations. If you will create animation record after every one iteration, velocity contour, preview it, make it visible to our views active. Record after every 10. I'm selecting 10 because it will create a lot number of frames. Click on OK. Okay. Now since it is initialized, let us just run this particular problem. Let me just check the value of initial. Let us just calculate this particular problem for 500. It will take a lot of time. Let us just calculate it for 200 iterations. Once it starts, you can see the residual values. You need to make sure that these values are going in the downward direction. It shows that our solution is getting converged. If it is moving in the upward direction, that it means our solution is getting diverged. You can see here a flow is being established now. You can see these values giving you certain logical numbers now. Earlier it was 672, now it is 264. Air is flowing through this particular exhaust fan. And also, you need to make sure that the system has enough capacity to handle the amount of cells that is being created after meshing. If it has a lot number or lot many cells, then this solution will be taking a lot of time to get solved. And also one thing I want to share with you that we have selected the z-axis, and by default the direction of rotation, that is anti-clockwise or clockwise, is the right hand thumb rule. You need to just place your hand, right hand, and the thumb of your right hand in the direction of the axis, and in the direction in which you are rotating your fingers, it will give you the direction of rotation. So in this case, if you just see from the z-axis, the fan is moving in the anti-clockwise direction. And I will show you how you can change the direction of rotation. Let us just see if once it is being done for 200 iterations, it will not take a lot of time. Now we are solving this using a simple algorithm. We will solve it for with coupled algorithm as well, and I will show you the difference between that. You can see here the residuals, right? These are getting constant. Once you get these constant values, it shows that there is a very small difference between the previous value and the next value. So it means that our solution is getting converged. Okay. Once every value gets close in terms of 1e minus 3, it will automatically stop, and it will show the solution is converged. You can see here that the magnitude has now reduced from 600 meters per second, which is not reasonable, down to 11 meters per second, which is a reasonable value, after 170 iterations. Now you can see that the value is not changing much after every iteration. It is 11.08 right now, the maximum value. 10.92 now. Now let us just see the animation, how the flow was happening. You just go on the results and under the animations option, playback, and you will see how it was happening. Okay, it was happening quite fast. So what you can do is you can reduce the replay speed. Okay. Now, suppose you want to see the vectors, velocity vectors, you can select on the vectors. It will be selected in the velocity vector by default. Click on the plane on which you want to observe. Since it is a plane, you just don't need 3D arrows. You can select arrows, reduce down the scale to 0.5, and this display. Now you can observe the direction of flow. You can see here air is coming from this side and getting expelled from the this side. Similarly, in the downward direction, since this is a wall, we have made it a wall, there is a recirculation. The flow is getting recirculated because of this wall and coming again to this exhaust fan. Okay. Now, what we will do is, let me just for the to show you all and just visualize this particular vectors because I want to show you how you can change the direction of flow. So it is coming from this direction to this direction. And this is also depends upon the profile of the fan or the blade which is there. If it is able to produce flow in the opposite direction. Sometimes it happens that certain fans are there, like the axial fans, they produce only the flow in only in the axial direction or in only one direction because of the profiling. Let me just show how you can change the direction. This is not a very difficult task. What you just need to do is you just need to place a negative sign before the rotational value. Now, what it will do is, by default, the directional rotation direction is in the by the right hand thumb rule anti-clockwise. If you are placing it a negative sign, then the fan will rotate in the clockwise direction. Let us just see like how it is rotating now. Okay, so we have just put the negative sign before the RPM value, clicked on apply, close. Then again we need to initialize it. Click on initialize. Yes. Now it will ask that you want to clear the history of the animation. Since you have initialized, new animation will be created. Okay, we will click on OK. Now we will run the solution for the same amount of iteration. Now currently the velocity is in from left to right. Okay, you can see here, which is generally the case. Exhaust fan express the air in the backward direction. Now you can see this. Let us just see how it is happening now. You can stop at this point of time as well. You just because we just need to see the vectors, velocity vectors. So let us now observe the velocity vectors. You can see here. Now in this option also the flow is from the left to right, because it is due to the profiling of this fan. It is designed in such a way that uh, if it rotates in the clockwise direction or in the anti-clockwise direction, the flow will always be from the left to right side. Okay, with different values. But this is the way you can visualize the solution. Now, what we will do is we will see this solution through coupled method. We will turn off the global time step because we don't want this to take place. We initialize the results. Yes, we have initialized the results, run the calculation. Now you can see that I have used couple method. The iterations are happening slower as compared to the simple method, but it will give you better result than the simple value, and it will the solution will converge much faster than the simple. Let us just see. You can see here, na? When we use simple method, the maximum value after 10 iteration was 600 something. But now it is 83. So it is much closer to the actual value when we compare it with the simple algorithm. And the results are what you are observing are the results are much better than the simple algorithm. Now you can see here now the flow is moving like in this direction. Can anyone tell me why? Let me just tell you because when we were cleaning up the geometry, there were certain round corners here. Okay, and this is because of those round corners. The flow is happening in this way. So this is all the important thing that you need to take care of based on the profile, based on the requirement. You need to clean up your geometry. You can, if you if you delete some feature which was important for your analysis, then you may end up having irrelevant result, or which are the result which were not which were missing certain aspects of the analysis. You can also see, the difference between the flow pattern in coupled algorithm and simple algorithm. Let me just stop it after the after 100 iterations. I will stop and we will now what we are currently doing by creating this plane and seeing the contours and the velocity vectors is we are post processing the results in ANSYS Fluent. Okay, and there is also one tool which is CFD Post, which is also used for post processing the results which are created by CFX solver and the Fluent solver, and it has better visualization techniques available so that you may post process the results in a better way. And but if you want to create animation in CFD post, then you need to save your results after certain amount of iteration. Then only it will be able to fetch up those results as per the amount of iterations you have saved. Okay. Let me just stop the solution or the solver after 100 iterations because we are running short of time. Now it is being done. Let us just observe the vectors. Save and display. Yeah. Now you can see it has captured the flow velocity or the count vectors properly. Now you can see the flow is happening from the right side to the left side. So this is also depending upon the solver which you are using, not only on the profile but also on the solver. By sharing with you all, I need to share with you that there are various factors which impact the results that you obtain. The profile, the solver, the algorithm, the method, the controls which you are using. Okay. Uh, so for post-processing your results in ANSYS Fluent, you can simply do this here in ANSYS Fluent. And suppose you want to do post-processing in CFD Post. So for that, what you have to do is first you need to save your result uh, in the form of data. The results are the files having the file format for results produced by Fluent is .dat.h5. So first you need to save your results. What we will do is we will save meshes without writing the case file. So it is saying because since we have changed the mesh, we need to save both case and data. The case is nothing but the solver setup or solver input that we have given, and data is the results which are produced after the solving of the particular setup. Done. Now we have written our results. Let us now open CFD post. Okay, now post CFD post is open. We need to load the results. We will go to file option, load results. Select our result which is there. Let me just click it. Even data, sure. This is the data that we have created. It's 1022. Yes, this is the data. Just open it up. Okay, you can see here that the geometry is being drawn here in the wireframe. Okay, you can zoom in, zoom out using your mouse middle scroll key, and you can rotate it by holding down the scroll button and moving it in the direction, whatever new direction what you require. We have options like vectors, uh, contours, streamlines, particle lines, volume rendering. We can create a point, line, plane, volume, isosurface, isoclip. Let us just draw an isosurface to see how velocity is flowing in our through the exhaust fan. We will select a certain value. Let us just select a value of 2 meters per second. Okay, let us see. Now you can see here how is the velocity happening. This is the isosurface. Isosurface are nothing. It creates a surface of a certain value, the magnitude which is there inside your fluid domain. If I just, you can see the values is ranging from 0 to 9.43. If I just type in 4, it will show you the places where the velocity is having the magnitude of 4 meters per second. It is getting close here. And if I just select the maximum point, it will be close to the exhaust fan because maximum velocity will be there only. You can see here, it is on the blades of the fan, blade tip. Okay. If I just select the value of zero point 0.5, so it will be spread across whole of the fluid domain, which is being stationary. You can see here. Air velocity, the magnitude of air having zero point 0.5 meter per second is spread across most of the fluid domain. Similarly, you can check for 1 meter per second also. You see. Okay, so this is the isosurface. Now let us see the velocity contour like we did in the ANSYS Fluent. We need to click on contour, all domains, location, fluid domain, variable velocity, velocity global value, number of contours. We can just select 10, click on apply. Okay, so we have drawn this fluid here. So what we can do is we can make a plane. Let's just draw a plane and we see the values on that particular plane. So you just go to location, plane, plane one, what you can just name whatever you want. We want a plane in YZ plane. Okay, so you select YZ plane. Okay, so just draw a plane. Yeah, you can see it has been drawn in the middle part. Let me just hide this point here. Hide this isosurface, and this is the plane that we have drawn. Now what we will be do? We will be observing the velocity contour on this particular plane. So we have already made contour. We will select this contour. We will select the location as the plane one instead of the fluid domain. You can just click on apply. You can see the velocity contour here in this particular plane. Likewise, you can make a number of planes and observe this velocity values on those particular planes. Okay, you can also change the view of this legend, but which is showing values in scientific terms. You can do that by clicking on default value, clicking on variable option. If you want to just make your variable visible, which is the velocity or pressure, whatever variable you want, you can select the fixed option. You can select the precision, that is how much values you want after decimal. And selecting two, you can select whatever value you want is visible. So you can also change this legend view. You can also change this orientation: X left, center, top, bottom. You can say select horizontal, vertical, whatever you want to observe. You can make this also depending upon your requirement. Okay. Let us now observe our one vectors, velocity vectors. All domains, location, we select the plane, vertex, velocity, yes, position none, color, dot variable, symbol. You need to select this normalize. Let me just show you the difference. If I apply it now, you can see like the values are very less and they are not very visible to use. So what you can do is normalize these symbols. Now you can observe them properly. Since this is a lot many arrows you can see, you can reduce the symbol size. You can also reduce this further for your easiness. Okay, you can see here this flow is happening in this direction. There is also recirculation. So this is it for today from my side. Uh, Hope you learned a lot many things from these 2 days workshop. I would request everyone just to share a small feedback about the workshop. And if you want to know further about the training that we are organizing, you can just connect with us on this particular number and mail. Okay. So I would request everyone to put down your questions and feedback on the chat box, and I will be very glad to answer those questions and respectively. Any questions, anyone? You have any trouble or you want any guidance? Can share the company list of CFD. I think you are there in the WhatsApp group. I will share the list in the WhatsApp group. Okay, sir. Any questions, anyone? You can ask questions related to any type of question related to CFD. Thank you. Thank you. Um, Where you can get this Faisal, let me just share you a link. Okay. I have shared the link in the chat box. You can download the student version of ANSYS from this particular link. When will I get the certificate? once you fill up the attendance form, I guess Imran can answer this more in a better way.
Allow me a few seconds. I am sharing the attendance form. So yeah, really sorry. I am just saying.
Sam, yeah, Imran, please go ahead.
I am just sharing in a couple of seconds, and you can fill it, and I will provide that certificate by the end of this week. So yeah.
Okay, Imran, thank you. Thank you for that information. At Sham, my system is having six physical cores and six logical cores. So basically, I have 12 cores, and graphic card is the GTX G4 GTX 2050 Ti, I guess. Let me just check once again. Yes, it is 1650 Max Q design. So basically, it's a gaming laptop. I'm using it for simulation purpose because it can handle certain simulations, small simulations. Okay. And how would you model a cooling fan in a thermal analysis? A SAF, you can model the cooling fan the same way I have modeled this exhaust fan. Yes, there will be different boundary conditions. There will be convection, there will be conduction, and for dedicatedly, if you want to perform cooling analysis for electronics, there is a tool called this ice pack, ANSYS ice pack, which is mostly used for electronics cooling. We can do that kind of analysis in that as well. Any more questions? Anyone?
Just an update. I already provided that link in the chat. Link is open, and you can able to submit it, and we will provide that certificate. So please provide that the name and your email address correctly. So yeah, so we will provide that with respect to the name provided by you, and those who are submitting will only get that certificate for this 2 days workshop. So yeah, thank you so much for joining for today's sessions, even on holidays, on Sunday late evening. So thank